Hi, welcome to Monday and chemistry. As you know, I'm out of PSSA testing and unable to be with you guys live to do the remainder of your lessons in the States of Matter unit. So I'm coming to you with a recording. This is my first try at doing something a little different. So bear with me if it seems a little awkward or, not looking at you a lot, or there's some bugs I'm going to have to work out, I know for sure. In any case, I hope all is well. I hope you had a nice 3-day weekend. And we're ready to get started with lesson 10. So we're talking about states of matter still. We're doing part 2 of lesson 10 today. Remember that let me just see where I am here. With the Lesson 10, Ideal Gas Law, we also study the Combined Gas Law. We did that on Friday. We went through several examples of the Combined Gas Law, which looked like this, where we had Boyle's Law, Charles' Law, Gay-Lussac's Law, all smushed together, and solved several of those problems. None of them were actually on your practice worksheet. Today we're going to finish up that practice worksheet number 1. There's a final area on there entitled Lesson 110, the Ideal Gas Law, and you have, I think, 4 or 5 questions on that. So I will go through all of those today, and hopefully throughout this video it'll pause automatically and you'll be asked for some feedback there. So just like in class when I ask you for chat answers or when I ask you for multiple choice polling answers, I'm going to expect that you do the same thing. And depending on how the technology goes, as I said, I've not used it before. I don't know if you'll be able to advance without doing it or not, but in any case, I should be able to pull a report at the end as well. So it's a great thing for me to see how you are doing in my absence. Okay, and maybe something good for the future, for all the time instruction. I don't know. We'll see. Okay, so we're picking up with the ideal gas law, and you see that in the mastery map here, we're talking about a new variable. That is the amount of moles. We're going to call that variable n. And n is going to stand for number of moles. Everything else stays the same. We have pressure, volume, and temperature, except we're not dealing with an initial and a final state. We are dealing with just the pressure, volume, and temperature of whatever gas we're looking at. So we are going to look also at comparing and contrasting a real gas, what a real gas is, what's an ideal gas, what does it mean to be the ideal gas law, and solve problems finally using that ideal gas law. So the very first thing we want to address then is what is a real gas and what's an ideal gas. And there's a few things that set them apart, right? Just like we live in reality, we have this ideal version. Maybe relationships are another good place to start when talking about this, because we have real marriages and then we have this picture of what we think marriage should be, or real bodies and this ideal body image. So there's a lot of things in our life that we can relate real versus ideal, and they're not the same. Especially in the case of body image, we have real bodies. They still have legs, arms, bellies, heads, hair, eyes, all of that. But in our ideal version, all of those things look a specific way, and they are a specific size or whatever the case may be. Same thing here. Gases are gases, right? Nobody's squabbling that. They're not solids, they're not liquids. However, there are some properties of them that we have assumed, or we do assume when we study gas laws, that are not necessarily the case in real life. The first of which is that gases occupy very little, if any, space. Every piece of matter in the whole world, solid, liquid, gas, plasma, occupies space. So that's the first thing we can discount. A real gas occupies some amount of volume. Now, the molecules might be very, very, very small, but they still take up space. We've learned that a gas is mostly made up of empty space, and that empty space is also very real, the space between those molecules. Okay, real gases we've talked about gases so far moving and bouncing off of the edges of the container and off of molecules themselves, but we've said they're in constant motion. And I don't think anybody has ever asked me, well, Mrs. Gross, do they ever stop? And according to the ideal gas law and this idea of what an ideal gas is, the answer is no. They constantly move forever and ever. Whereas in a real gas, we know that there are some conditions in which they do stop momentarily. And by momentarily, I mean, maybe a micro or a nanosecond. something causes them to stop. They don't stop permanently, necessarily, under most conditions. We've talked also about collisions in the properties of gases. Collisions create pressure. When those molecules are bebopping all over the place and they're hitting the walls of the container, when they're hitting each other, those are called collisions. And in the ideal world, there is no energy lost in those collisions. So they just go, and you can run around the room, hit the wall a million times, you're not going to lose energy. It's impossible in our real physical world, because if you run into the wall, you're going to at very least hear noise. If you don't have pain, you will hear a noise, and noise is a form of energy. Most often we're talking about energy being lost as a form of heat and light. In those real gases, collisions are not what we call elastic. They're not perfectly elastic. You're thinking about playing pool on the billiard ball table, and you knock into that white ball, the white ball hits the triangle, and they all go boom, right? They all make noise. And then there's friction between the ball and the carpeting, whatever that's called, the felt on the table, right? So you're losing energy all over the place. We can approximate a gas molecule in its behavior to billiard balls. So we do lose energy in the form of heat and light, just like we would have sort of in reactions. And finally, probably the most notable difference between real and ideal gases is that in an ideal gas, there are no attractive or repulsive forces between particles, and we know that that's not true. Right? We have studied way back, think back to December, when we studied about chemical bonding. And when we have covalent bonds in particular, for example, let me see here. For example, HF. Whoops. Okay, here we go. For example, HF. We said when we have H in anything, and we can also look at water, right? H2O. Hydrogen is going to take on that partial positive charge. They end up acting really like ions, because then we have a partial negative charge on the other very electronegative atom, in this case either fluorine or oxygen, and nitrogen does this as well. And what we said happens is that these molecules will line up with each other, so we get another hydrogen from another HF molecule interacting in this way, where we have an interaction between the partial positive and the partial negative of two neighboring molecules. That's an interaction. We call those intermolecular forces. And you should recall that they are a huge, huge, huge piece of chemistry. Not only are they hydrogen bonding, a specific example of hydrogen bonding, but they are also an example of dipole-dipole forces. And those London dispersion forces we talked about don't even have to have particularly electronegative atoms in them. They just have electrons moving around all the time. Okay, so that's sort of like the theory behind an ideal gas versus a real gas. And what you need to know is that these differences exist and nothing really beyond that. All the gas laws, Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, and the ideal gas law all follow this principle that gases behave ideally. You know, it's kind of like real women are not Barbie. So real gases are not ideal gases, but we're going to pretend they are for the sake of chemistry. Okay, so that brings us to the mathematical portion of the ideal gas law, and that is an equation that looks like this. We have PV equals nRT, and most of these should be probably pretty straightforward to you. You have pressure, P, volume is V, T is temperature, and that of course is in Kelvin, and we're not going to forget that. It's a very important piece. We always convert to Kelvin whenever we're doing any gas law. But then we have two new pieces in this equation. The first piece is N. N, as we said, is going to be the number of moles of a gas. And in this equation, it's the first time that we're addressing the what the relationship is between the amount of gas in the container and its volume, the amount of gas and its temperature, the amount of gas, and I'm talking number of molecules. So up until this point, we looked at amounts using volume, size. but we never changed the number of molecules in there. So N is going to stand for the number of moles. And then we have temperature, R. R is what we call our gas constant. The gas constant is exactly what it says. It's a constant. It's only used in this particular gas equation. It's a number, and as you can see below on this slide, it can be either 8.31 liter kilopascals per mole Kelvin, or it can be 0.0821 liter ATM per mole Kelvin. Those units are very, very important because the number we use, those two numbers are 2 orders of magnitude apart. And by that I mean we're looking at 8 versus 0.08. Okay, the numbers after that are very similar, but that's the biggest difference. One is 100 times bigger than the other. We determine which one of those we use based on what pressure there is listed in the problem. So you'll see liters are the same in both of those R values, moles and Kelvin are the same, but pressure is different, and that's because we can measure pressure in so many different ways. We do not have an R value for torr or PSI or millimeters of mercury. So if I were to ever give you those types of units to work with as a pressure, which I won't, you would have to convert back to kilopascals or ATM to do the gas laws, because that's the only value that we provide in R. It's the only one that exists. In the problems that follow, you'll see how we're going to determine or pick from each of those. Okay, so we're going to jump in and I'm going to do an example, and I'm going to do it start to finish. I probably won't stop and ask for any questions along the way. So I would like you to work along with me. Go ahead and open your worksheet. This is going to be number 3 in the section entitled Lesson 1.10, the Ideal Gas Law. The first 2 questions have to do with everything we've gone over so far. What's the mathematical expression? What do all of the variables mean? And so on. Okay, problem says, if you have 4 moles of a gas at a pressure of 5.6 atm and a volume of 12 liters, what's the temperature of that gas in degrees Kelvin? So we can go ahead and identify our units. Our units will lead us to our assignment of variables. So we have ATMs, we have moles, and we have liters. That means that we know, first and foremost, 4 moles is going to be our N value. 4 moles. Please excuse my handwriting. And then we have a pressure of 5.6 atm. And we know that it's pressure because it's ATMs. And we have a volume of 12 liters. Now we're left with R and T. And the question is, what is the temperature? So we can go ahead and question mark that. That's our unknown. And we still don't necessarily know what R is, but R is a constant. So we're going to pick from one of these 2 guys over here. And again, we're going to have to look and see what pressure units we're using. And in this particular problem, we have atmospheres, ATM. So we're going to go ahead and use the R value that has ATM in it. And so that means our R value is going to be 0.0821 liter ATM per mole Kelvin. That's how we say that. Okay, now we just need to plug and chug, and as always I would recommend you rearrange your equation first to solve for what you're looking for. So here we're solving for T, and algebraically, to get T on one side by itself, it's most easy glitch. It's most easy for us to divide by NR on both sides, okay, and get T, a new equation for T. It's going to be PV divided by NR, and now we're just substituting in. So now we're saying that we have pressure of 5.6 multiplied by our volume is 12 divided by 4 times 0.08. and that's going to give us our temperature in Kelvin, and it will give us our temperature in Kelvin because we have Kelvin units in our R value. So if I were inserting all of my units here for R, you would see how that they cancel, but I'm not going to do that right now. Okay, so I need to pull out my calculator, and of course order of operations says we do the top first, and we solve for 67.2 on the top, divided by 4 times 0.0821 is 0.3284. And that equals T. So we go ahead and do that math. Oops, I have my mouse over here. 67.2 divided by 0.3284, 204.6. So we'll just leave it 204. Okay. Temperature is 204. Is it a reasonable number? Can we check our math? We can check our math just by going through and actually checking our math. There's really no way, again, like we talked about with the combined gas law yesterday, there's really no way to affirm that we are sort of on the right track, that things are kosher, because there's really no rule here for the most part. Okay, so, but we know that typically Kelvin temperatures are in the 200s and 300s, sometimes 400s. All right, so that's the steps we're going to take to go ahead and do this. Now we're going to go through 2 examples where I probably will pause and ask you some questions along the way. Okay, we're going to move on to number 4. In this problem, it says you have an unknown quantity of gas at a pressure of 1.2 atms, a volume of 31 liters, and a temperature of 87 C. How many moles of gas do you have? So I'm going to ask you to go ahead and answer the question, what is our p-value? Okay, so p-value is 1.2 atms. And we know that because atmospheres are a pressure unit. And now what is our volume? Okay, volume is going to be 31 liters because liters is a volume unit. What is N? N's the next variable on our list, and it is equal to unknown. We don't know it. Question says, in fact, how many moles of gas do you have? Okay. Let's skip R just for 1 second and go to T. Are we given the temperature in this problem? Okay, yes, temperature is 87 degrees C, but we cannot use it as C. So please calculate for me the temperature in degrees Kelvin. Temperature in degrees Kelvin is 87 plus 273, which should equal, off the top of my head, 360. Okay. Okay. All right. So now our R value, pick the R value that we're going to use. And your hint is going to be that you have units of ATM in the problem. Okay, we are going to be using the second R value, again, because it has ATM listed in the units, and those units will have to cancel. I'm going to try this time to be a little bit more clear about that. So 0.0821 liter, and there's just so many things you have to write when you do that, right? Okay. Excellent. So now we're going to use our handy-dandy ideal gas law equation. We have PV equals nRT. And in this case, we're not solving for T. We're solving for N. So again, just to isolate N, we're going to divide both sides by RT. And that cancels on the right. We get a new equation for N. The equation for N goes something like this. N equals P times V divided by R times T. I'm just sort of condensing it there so I have plenty of room to write. Maybe if I change the thickness of my pen, that would help, huh? Pressure is going to be 1.2 ATMs. We're multiplying that by a volume of 31 liters. And then we're going to divide, and we're going to divide by that gas unit, that gas constant 0.0821 liter ATM per mole Kelvin. And those are units, okay? So we're multiplying there by our temperature, which is 360 K. Now, please pay attention to the way the units cancel. We have ATMs canceling ATMs. On the bottom, liters and ATM are a numerator within a denominator. So there's a fraction within a fraction there, right? But ATMs will cancel and liters will cancel in the same way. Now, in the denominator, we actually have kelvins canceling, right? Because we have a denominator in the denominator multiplied by Kelvin. And we're left with moles, and that's because it's a denominator in a denominator. So it ends up being on the top. It's not units of inverse moles or moles on the bottom. The moles do end up being on the top. All right, so if we calculate this out, on the top we have 1.2 multiplied by 31, and that solves to 37.2, divided by our gas constant multiplied by 360, and I get 29.56. And that solves to be something greater than 1. .26. And of course we're solving for moles of whatever gas this is again. Okay, so it's important you keep track of exactly what those variables represent and what you're solving for. Good, excellent. Let's do another. Number 5 is really more of the same, and you have a temperature conversion. So I'm going to ask you again, give you just a second. We'll read through this problem. It says if you have 7.7 moles of gas at a pressure of 0.09 atm and a temperature of 56 degrees C, what is the volume of the container that the gas is in? Okay, so let's start there. What is the volume of the container? You should always really be paying attention to the question maybe first and foremost, because it usually tells you what your unknown is. So your volume is the thing that's unknown here, question mark. And what's the pressure? Pressure is 0.09 atm. What's the number of moles? 7.7 moles. What's the temperature? 56 C. But we know we have to convert that to Kelvin, so we add 273 there, and we get a temperature of 329, I believe. Okay, I'm not doing that in the calculator. That's all in my head. So if it's wrong, go ahead with the correct temperature in solving this problem. Now tell me, which R value are we going to use? You betcha, you are going to use the same one we have been using because it has ATMs in it, and our problem has ATMs listed in it. So our R value is going to be 0.0821 and blah, 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 blah. You know the units there. I've shown you the units now, so I'm going to keep it out of the mix from now on. And I don't have, oh yes I do. Okay, so we're going to use our ideal gas law equation, PV equals nRT, and this time we are solving for volume. Okay, so we haven't solved for volume yet. To solve for volume, we're merely going to divide by pressure on both sides. Pressure cancels, and we have a new equation that goes something like this. V equals N times R times T, all divided by P. Substituting those values in, N is equal to 7.7 times 0.0821 times 329, whoops, 329, all divided by pressure, which is 0.09. And when we crunch those numbers in real time, on the top I get 207.98. So I'm going to hang on to those two digits for now. And we're going to divide by 0.09. And the volume I get is 2,310. We're looking at using liters as our volume measurement. If you needed to know why or how, you go back to your R value, because whatever you're left with is coming from your R value units. So that's going to be liters equals volume. Okay? That's a lot of liters, but I've done this a couple of times, and so I know it is the correct answer. Excellent. Now, try one yourself. This is just like we would do in class. Read through the problem, identify your unknowns, and log your answer. Okay, how many moles of a gas are in a sample on a 5-liter container at 298 K and 200 kilopascals? There is no temperature conversion necessary here. Right? We're just doing PV equals nRT. We're solving for N. So our equation gets rearranged from PV equals nRT to divide by R and T on both sides. That cancels on the right. N equals P times V divided by R times T. Our pressure here is going to be 200 kilopascals. Our volume, 5 liters. That whole quantity divided by 0, which R value we're using. Our pressure is in units of kilopascals. So this is the first time in this lesson that we're going to use actually the other R value, the 8.31 R value. Okay, so R is 8.31, and we multiply that by our temperature, which is 298 K. And we crunch those numbers, we should get 200 times 5 is 1,000 on the top, divided by 2,476-ish on the bottom. That's going to be a number less than 1. I get a N value of 0.40 moles. So if you answered B, you are correct. Yay, hopefully you got that. And you can see I've given you a few different options there. Each one of your options was a different magnitude, so maybe you did something wrong with your decimal place. And if you got a totally different answer, of course you were answering D, none of the above are there. But B is the correct answer in this case. Okay, next question. Try your hand at it again. This is also still on your worksheet, number 6. Read through and choose from the options listed. Alrighty, so we're using the ideal gas law. We do have units of Celsius here, so we're going to have to use our temperature conversion. Let's go ahead and label our PV equals nRT over here, maybe on the side, P, V, N, R, and T. Pressure is going to be equal to, we don't know. What is the pressure of the gas? So that is our first unknown. The volume of the gas is 88.89 liters. That's a lot. We don't usually work in volumes that big. The number of moles is 17. Temperature is 67. We're going to add to that 273, and we're going to come out with 340 K. And our R value, well, what's our pressure? Oh, this is a trick question. This is a tricky question. What R value do we use? I'm not making you answer that question because this is a teaching moment. If we don't have a pressure listed in the problem, we don't really have to pick an R value because the R value is totally chosen based on what the pressure is in the problem. So the answer here is you can use either of them. So let's just pick one. First, we're going to use 8.31. I'm going to do it both ways, and we're going to see what happens here. We're going to use the 8.31, and we're just going to make a note that that's in units of kilopascals. Okay? We're solving for the pressure of the gas, so PV equals nRT divided by V on both sides leaves us with P equals nRT divided by V. And we're just going to substitute in our numbers 17 times 8.31 times 340, that whole quantity divided by 88.89. And that pressure then works out to be, pardon the time it takes for me to do this, but I like to do it with you. We have a 48,031 on the top and 88.9 on the bottom. 540. 540, and this was in units of kilopascals, so our answer is going to be in units of kilopascals. I'm going to go ahead and highlight our R value blue, and I'm going to highlight this answer blue so that you know they go together. So what does that work out to? That works out to answer C here. So if you answered C, you are correct. Can you do it the other way? Absolutely. So I'm just going to change my pen color here to green to show you that I'm doing it just slightly different. I'm going to use the same equation though for the next part. So my pressure is equal this time to 17 times 0.0821 multiplied by 340 divided by 88.89. And rather than show all the steps there, I'm just going to go ahead and crunch those numbers. And we have 5.3. And that's in units of ATM. We're going to highlight those differently because our R value has pressure units of ATM in it, and that's the only thing that makes those different. But do you see when you use those two R values how different each of your answers is? We have 540 versus 5.3. That's 100 times different. And the reason it's 100 times different is because our R values are a magnitude of 100 times different apart. Okay, so that was 5. Oh, that didn't work. Let me get rid of that. 5.3. Okay, so really the true answer to this problem is D. Both C and, that should say B. Both C and B are correct. Because when you're not given pressure, whenever you're solving for pressure, you can solve it any one of two ways. And I'm not sure you'll see a situation like that on a quiz or a test, but I did want to introduce it as a possibility. Okay? That pretty much does it for examples that I can show you. We have looked at 5 different examples in class today of ideal gas law, and you have them written down as notes. You additionally will have more practice in your 1.10 quiz. When we end here today, I would like you to answer this in the box there. Would you use for a situation, sorry, jumping ahead of myself, you are given the temperature, volume, and pressure of a gas, okay? And you need to determine how much gas you actually have. What equation are you going to use? We've learned about a lot of them now. We have 5 gas laws. Boyle's, Charles, Gay-Lussac's combined in ideal gas law. Which one is it? If you said ideal gas law, you are A-OK, awesome. Because ideal gas law is the only gas law that has N, the number of moles of a molecule. A number of moles, again, are just like the dozen. They tell us a number of a group, and ultimately from that we can determine individual particles if we wanted to. Okay? Excellent. It's the end of Monday. What I want you guys to do today, or what you should be doing, is now completing your 110 quiz. And that quiz will have, I don't believe there's 10 full questions on it. No, there's not. I think there's like 8 questions. One of those questions is worth more points than 1 point. We have 3 examples of combined gas law questions. We have 3 examples of ideal gas law questions, so you'll have additional practice there. Don't forget the quiz allows 2 attempts, so if something goes wrong the first time, please revisit your gradebook grade and see which questions were wrong. We do allow you to see the incorrect questions. Try them again on scrap paper first, then go back into the quiz and fix them up. Your next installment video will be on lesson 111, which is about absolute zero. I hope you're having a great day. I trust that I am ready to come home now, since you guys are probably watching this in the afternoon, hopefully during your chemistry time. I'm probably tired of testing by this point. I can predict that already at Monday at like noon, 1, 2, yeah, I'd be checked out. See you guys tomorrow.